Okay, go back. Okay. Yeah. Okay. Good morning, everybody. Thank you for joining us today. Give me 1 minute. I'm still letting a few people in that are trying to join. I am going to mute everyone as well. We encourage you to participate and get involved in conversations. I'm just trying to eliminate the background noise. Here we go. So welcome to our second workshop on modeling HVAC systems with RETScreen Expert. Today we have a bit of a hands-on session. So if you joined us last time on October 30th, we went through a bit of a demonstration of different scenarios. Today we'll be doing hands-on practice. Everybody who registered should have received a temporary RETScreen key via email last week, but in case you did not, I'm going to share that in the chat here as well. And Stephen and Michelle, our guests today, have also prepared a quick document that just shows what's on the screen for each of the scenarios we're going to be working through, and you can pull that up on another screen and follow along.
Megan, were you going to drop that in the chat? I don't see that here.
Yeah, it's just giving me a hard time.
Okay. I'll keep admitting people as you're focusing on that.
Thank you.
Well, while you're doing that, Megan, I think what I'll do is just describe the agenda, okay?
Yeah, that sounds great. Thanks.
And even if that isn't successful, we still have sort of a backup client plan because we'll display each of the activities on the screen. So welcome everybody. Stephen here, Michelle and I are going to facilitate. I'll start off and Michelle will sort of dig into some of the details of the HVAC, and then I'll finish off with, if we have time, with a fifth activity. So I'll talk a little bit about what are the elements of how you actually model HVAC within RETScreen, and in difference to, or different from other software, there are not pre-configured systems. So you have to take the tools that are in RETScreen and actually pull them together and create the model that works for your situation. So we're going to run through 5 different scenarios if we have time. And they're very similar, but they're different also in a subtle way, which can make a big difference to the outcomes. So, and then if we're finished, we'll have some Q&A. But I'm going to suggest, as we're walking through, we've got about 35 people online. I don't know how many of you will actually be walking through RETScreen with us, but we encourage you to follow us through the examples. Once Michelle begins, we'll start. Actually, he'll probably just say, okay, let's start a new file, and we'll go through the protocol for starting a new file. And he will build the file from scratch, right down to where we specify the climate data station, that is external conditions, the prices of the commodities, the fuel and electricity we're using, and then building up the system step by step. There's going to be similarities between the systems, so a little bit of repetition at the beginning of the setup. Michelle, maybe you can economize by saying maybe in the third or fourth one, depending on the time, you can simply just use the same file but modify it for that purpose. So I'll let you make that decision. So as we're going through this, I don't want people to get stuck. If you are trying to follow through and you do have a problem, I'm going to ask you to, I would say, Megan, if you can keep an eye on the chat, but if you really need help, just open up your mic and say, hey, I'm stuck here. We'll try to make a decision as to whether we dig into it. Others may be having the same challenge, but we do want to try to make it as hands-on and as skill building as possible. So, I always start off my RETScreen sessions with this, that RETScreen is a fairly comprehensive decision support tool, and it is available in 38 languages, covering 2/3 of the world population. I like to think of it as a toolbox, an all-in-one toolbox. It has, in many cases, for many of the projects I work on, for the matter, has all the tools I need in one place. And even if it doesn't have a tool that I need, it has connections that we can link to other tools, but it also has a place where we can place, and Michelle, maybe you could demonstrate this, take a screenshot of a hand calculation you're going to do in one of the examples, and you can place that in the notes section of RETScreen, just paste it in there. So even if you do something outside of RETScreen to support what you're doing in RETScreen, you can always record that, which makes it really useful when it comes to other people later on looking at what you've done. RETScreen is supported by many organizations today. We, acknowledge the Independent Electricity System Operator here in Ontario, or ISO. and the Save on Energy program. They have contributed over the years to the development of this tool in a number of ways, and we're certainly using it in our efficient electrification initiative as part of the capability building program from Save on Energy as well. So that's really the context of today's session. I really enjoy using the weather data that we can get from NASA via the links, either daily or hourly. So, as I said before, it's a toolbox with everything in it. Do you take every tool out every time out? No. Do you use one tool for everything? No. So what we have to do is figure out which bits and pieces we're going to use in the circumstance that we're in. That's always the challenge of using any tool like this, especially RETScreen, is how do we abstract from reality? We got a situation, it's physical reality out there. How do we abstract from it and actually represent it fairly in RETScreen? That's the key. How do we represent that situation, both from a structural standpoint and then from a numerical standpoint? I'll take you through that one in a second. There's lots of help. Again, if you don't see how something is done today, there are lots of case studies and project templates in there as well. There's online help, there's videos. Many of the modules we'll use today, there's a little video to go along with it to explain how to use it. And actually, I should come back here. There's actually, on the virtual energy analyzer, there are literally hundreds of building configurations, archetypes, right? Very typical situations. That's the definition of the word archetype, but also archetypical projects too. So some of the projects that maybe we won't touch on today, you can find in there as well. So case studies and templates down here, and virtual energy analyzer, great starting points. Really see how the experts have used this tool, how you can use it. And some people even take those virtual energy analyzer archetypes and actually do a virtual energy audit of their building, sort of scaling it and matching it to their circumstance. So, but today we're going to dig down into a little more detail and get into the HVAC systems. When we're modeling HVAC systems in RETScreen, we have to deal with a number of models. We have to deal with the heating equipment or heating system, the cooling equipment or cooling system, and we typically have to deal with ventilation models. Could be a more detailed version. Today we're going to mostly use the detailed version, but then we also have a simple version as well that we would use, which simply, in energy technical terms, what's behind the ventilation models is simply CFM delta T 1.08 or liters per second delta T 1.2. Now, in the simple model, level 2, that's actually played out pretty clearly. But in the more detailed version, which has a number of different options, it can resolve to that simple thing, but there's a lot of sort of attachments that actually make it adaptable to different circumstances. So what I'm going to do is, just as we begin here, I am going to open up RETScreen. I'm going to open up the sample situation that I presented last week with the slides, but I'm going to open it up and just walk through the different elements. So I'm going to do two things. When I build a system in RETScreen, I like to approach it. Okay, let's build the structure first. What are the elements? And then go into each of the elements of the structure of the system or the building I'm modeling and put the details in terms of the numbers. So when we're modeling this HVAC system, we're going to need to have a piece of heating equipment, a piece of cooling equipment, a piece of ventilation equipment of some form, right? And then possibly a piece of electrical equipment, which is a motor driving that air handling system. So one of the things that's important to represent, once you put a ventilation system in RETScreen, you haven't accounted for the electricity that's needed to move the air. So we need to do that separately. So let me show you how that works in RETScreen very quickly. You're going to go through this many times here today. I just got to make sure I pop up the right one here. Here we go. Okay, so taking it from the top. So I'm on the energy tab, which I go to directly. There are a couple other tabs. You'll walk through these in the hands-on if you haven't done it before, where you pick the climate data location, you pick the type of facility you're working in. Sometimes this is window dressing, but actually this is the place, and I encourage people to use notes. There's lots of places where you can add your own pieces in here, and Michelle will use that once we get into one of the detail areas. Okay. So down the left-hand side, we need to have electricity and fuels, and these actually also flow across the top to some extent as well. So electricity and fuels, what are we using in this building, right? What are the schedules that we're using, right? And we can add schedules to our heart's content. We're not stuck with the 24/7. Michelle will use a couple of different schedules, I think, in your examples. Then we need a piece of heating equipment, right? So this is equipment that converts the purchased form of energy, which in RETScreen is actually called a fuel, right? And it converts it to the end use form of energy so that is, we take natural gas in this case and convert it to heat, which can then be used in the ventilation systems. The cooling equipment, likewise, takes electricity, which is also actually referred to as a fuel in RETScreen, electricity, and through the refrigeration process converts it to cooling energy, which can then go to providing cooling at the end use, which in our case today is going to be the ventilation system. So those are the systems that convert the purchased commodities into the end use forms of energy. And I'm using words very carefully here. When we get into a couple of steps further, I'm going to show you the results screen. And it's very important to keep your head about you in the results screen, because the term fuel and energy and where energy is calculated, where fuel is used, it can be confusing, but I'm going to try to make it fairly straightforward for you. All right, so now we have the end use system. So these are the systems that actually utilize energy. So in this particular example, right, that I'm looking at here, I have basically a rooftop unit that's providing ventilation. And here I've detailed all the information about that. In this case, we're not going to do this one today, right now, because Michelle's going to take us through this at least 4 times this afternoon, right, in different scenarios. So, but in a nutshell, we have a total amount of airflow, a ventilation rate, and then some details about how that plays out. At the bottom, RETScreen calculates for us the heating energy, the energy required in the base case to provide for that heating of that ventilation air, and the cooling energy. Now, that's not the amount of gas and electricity we use. That's simply the heating and cooling energy, the end use. We also, in this system, have a washer and exhaust system. So this is the method 2 ventilation, which is a lot simpler. Here we have a flow and a schedule, right? Very simple, all we need. And really, you can see CFM delta T 1.08, because the weather gives us the delta T in conjunction with the schedule, and we heat and cool this air, right? So very simple situation. This works in many circumstances. I will use this one if we get to it in the demand control ventilation example, because this is all we really need in that circumstance. All right, so how do we move the air? So now we need a motor, right? In this case, the motor had a measured power of 3.5 kilowatts. It operates for a certain number of hours in the base in the proposed case. So here we have the motor, right? So those are the elements that we need in most HVAC systems. We need a piece of heating equipment, piece of cooling equipment, at the very least a piece of ventilation equipment, and then a motor, right, to move the air that's moving through that HVAC system. All right, so what does the results of all this look like? And again, I'm not going to delve into the details of this one. I want you to just look at it from a sort of a big picture perspective. So on this, what we call the include screen, Michelle will refer to the include screen many times. As we move through the examples, right, we'll come back to the screen and have a look at the results of what we've done. Excuse me. So the include screen usually defaults to what's called fuel saved. Fuel, in RETScreen's terminology, is that which we purchase, right? Fuel is converted to energy by the heating and the cooling equipment. So in this case, we didn't change, in the base case and the proposed case, we didn't change that furnace. We didn't change that cooling equipment, right? So basically, right, when we look at fuel saved, there's no fuel saved at the heating or cooling equipment. Where the savings occur is at the point of end use, right? So this is what we call, this is the fuel that's saved, right? Because we no longer ventilate, and this is the fuel, or as much, and this is the fuel in form of electricity that's saved, right? Depending on what fuels we use, but in this case, electricity, right? And then this is the electricity, known as the fuel as well, by this title up here, right? That's saved when we reduce the runtime on that fan motor. Now, you may dive in here and you may go, I'm going to go and have a look at this ventilation system. And down here we have the heating energy, and here we have the energy saved. And here we have the cooling energy, and we have the cooling energy saved. Now, just make a note of these, okay? This is the heating energy, 27,600. Cooling, 4619. So 27 and 46, let's say, okay? Let's go back to our include or our summary screen. But wait a second. It says here 34 and 15. So the fuel saved on the heating side of it is higher, but the fuel saved on the cooling side is lower. Why? Because, I'll show you why, that's not energy. If I go to energy saved, now I get my 27, my 46. But remember, right, if I reduce the end use energy coming from a boiler, in this case, or a piece of heating equipment with efficiency less than 1, the actual fuel that I save is actually more. So the fact that when I go from energy saved to fuel saved, the heating energy goes up, but the cooling energy goes down is a reflection of the heating efficiency being less than 100% and the cooling efficiency, or COP, being greater than 100% or 1. So, you've kind of keep your wits about you when you look at the screen, but once you've done it a few times, which is what we're going to do, it actually becomes very intuitive, and it's actually useful to be able to look at those things back and forth nicely. So that's it. As from a structural overview, I'm not going to go into, like I said, the details of this one. Michelle will work us through 4 different examples where he will look at arriving at this result in different situations. Michelle, is there anything I missed there, or are you ready to take over?
Yes, we do have a question, Stephen, that you might have time to answer. It's about how do you get hourly weather data in RETScreen?
So for what we're doing right now, we're using what we call climate data. Okay, so I'm going to go back to the location screen, and down here, so all the calculations in what we're going to do today are simply derived from this external environmental data. In fact, what we'll end up using is the heating and the cooling degree days to a large extent. Okay, that's what's used in the calculation. These are monthly, but ultimately the way you have to think about it is RETScreen, in what we call feasibility analysis work, like we're doing, is going to do one annual calculation based on this breakdown monthly. Now, if you want hourly data, very, very good. All right, so to get hourly data, let's say there's a couple of reasons you want it. Maybe you simply want to compare the electricity consumed in the building from a demand profile interval data on an hourly basis, and you want to compare it to the weather, the air temperature outside. Or maybe you've got a location where you don't actually have a climate data station. You want to construct your own climate data by taking all that hourly data and basically making it into climate data. Where do you get that? All right, so we go over to the facility page, and I'm going to open up all the things across the top. Actually, if I click on performance, I'm going to see a place where I can get data. So that's the simple answer to your question. Go to performance, but you can get there also by going all as well, okay? So this doesn't get rid of what we had before, which was feasibility. So I go to my data page. All right, if I want to get weather data, then I click on weather, okay? And here, this is the location that we've selected in this file. This happens to be, I think, the downtown Toronto, one of the climate data locations in downtown Toronto. And then I click on advanced, and I click enable, right? Enable. This is sub-daily data, okay? So that means if I want daily data, I would get it without doing this. But if I want the hourly data, and now I click over, and so I'm going to get it from NASA, right? And then it's going to ask me where I want data from. So I'm going to get it from, basically, I'm just going to make this a short import because it does take a fair bit of time. I'm going to gather, I'm going to say from August until now. You can get as long as you want, but it takes a while. And as long as the Congress in the U.S. has appropriated these, or the NASA website's typically available. So, but we are taking data from the NASA from the world over. So, all right, so hourly data, click OK, and now RETScreen will download that hourly data, which honestly I find incredibly valuable. Beyond what we're going to talk about today, I use this in almost every project that I do. So there is our hourly average temperature data, and then from here you have in the analytics section places to do graphs and all that great kind of stuff. So I could actually do a time series graph right now of this. I can pick up the average temperature, maybe the minimum maximum temperature, and Bob's your uncle or Mary's your aunt. We get a time series graph. That's just for the weather. Hopefully that answers the question.
I'm sure it does. I'm sure it does.
All right, Michelle, over to you.
Okay, I'm going to take over the screen. So as Stephen said, guys, we're going to go through building actual systems. You'll remember in the first session we described 4 different types of systems that you could build in RETScreen. Obviously, you can build many systems, but those are different types. So we're going to go through those different types because there are some, I'd say, different strategies to really accurately define those systems in RETScreen. The first one we're going to do, and you may remember that one, is the makeup air unit system. And we will do that all together. If I go too fast, put it in the chat. Tell Stephen if I miss a step. Stephen, if I make a mistake somewhere, don't be shy. I know you're not shy, so just let me know.
No, I'm going to follow you. So if you're
going to follow me. So we'll build that step by step. And obviously, we'll also put a measure, and you'll see that the measure I put in all of the 4 systems, Stephen and I, we put pretty much the same measure so we can see the impact of the system definition on the economics of that given measure. It may not be the most economical measure to start with, but at least it gives you that relative impact of the system definition in RETScreen for that one specific measure. So we're going to start with that makeup area unit system. So I invite everybody to open a RETScreen file, a blank file. And you can define that file as being a feasibility study, just like Stephen had. So hopefully everybody's already at that page. You have feasibility, because the first thing we're going to do is define our location. We're not using the virtual energy analyzer. We're not going to discuss the virtual energy analyzer at this point. So we're going to build from scratch a feasibility analysis. And first thing we're going to do is select the right location. So I'm going to flip back to our page. So our location is in Canada, and it's Toronto. So you're going to go in here and you click on select climate data location, and you should all get this pop-up, and then you can actually type the name of the location you want in here. You can also drag the little icons you see on the screen. So I'm going to say I want Toronto, Ontario, and now it's going to...
I think we're going to go to Mississauga, right?
Yeah, and I don't want Mississauga. So I want Toronto downtown. So I double click on Toronto downtown, not the airport. It would not make a big difference. It's just so we have exactly the same answer, because honestly, it's maybe a bit colder at the airport, but because there's not the heat island effect that the downtown weather station would have. But, you know, it's just so that we have exactly the same result. So you select Toronto downtown by double clicking on Toronto. Now, if you forget and we have slightly different results, that could be the reason. So not a big deal. So if everybody has done that, you'll see that you should have here the exact same location as I have, and then you'll have your monthly data that is going to be used for all of the HVAC calculations. You can actually change that. When it's in blue in RETScreen, it's a value that can be changed. Be very careful if you change that. You should document it. There's many places in RETScreen where you can put notes, and you should document if you change anything in here so that you don't forget that it's no longer the default Toronto values. But we're not going to do that. Don't change anything. We're going to keep that. The next thing we're going to do, you're going to change tab, go to facility, and that is critical to do that. Otherwise, you will not have the proper menu to build your HVAC system. In facility, by default, you will have power plant. We don't want power plant. We're not defining a power plant. We're going to define a commercial building. And we're going to actually keep office building because it's one of the most common buildings you guys are likely going to work with. And actually, regardless of what you would pick, your menu for building your HVAC system would be the same. So, but just make sure you have office building. We're not going to enter an area right now. We're not doing benchmarking. So this area is of no use for us right now. So we're leaving that blank. And now we're going to go to the energy tab. And that's where we're going to start defining our HVAC system, just like Stephen had shown us before. First thing we're going to do, make sure that we have the proper energy rates. For the energy rates, we're going to enter the marginal rates. Obviously, in our sheet, we provide you with the marginal rate. It is important that you don't define your average yearly rate, because that rate is going to be used to calculate your energy savings. Therefore, it has to be the last tier or the last, cubic meter, which doesn't really apply too often for gas, but that's what you have to enter, the marginal rate on the last, kilowatt hour that you buy in the last cubic meter. So we have 45 cents and 12 cents. So we're going to enter 45 cents for gas and 12 cents for electricity. So we've got our location selected properly. We have our rate selected properly. Now, the next thing we're going to do is looking at our makeup air unit, if you collect the information on your makeup air unit, we're going to define the schedule that will eventually be associated with our makeup air unit. And that one is quite critical. You probably remember last time about schedule, what I said for a makeup air unit. You have to do it slightly differently than what you might think. So there is always a 24/7 schedule that is defined by default with no temperature setting, but we're not 24/7. If we go back into our definition here, our base case, it says that we are 16 hours per day, Monday to Friday. So what we're going to do is click on the plus sign at the top here in the schedule. So I clicked on schedule, then I clicked on plus. I'm going to actually give it a name that means something to me. So I'm going to call it MUA schedule, so that once I see it in my system, I know what schedule I'm using. And in the problem, it said, in the definition of the base case, it says that we're 22 degrees Celsius at all times. So we enter 22 and we enter 22 here. Now, for those of you who were there last week, did I make my first mistake? The answer would be yes. If you remember, we said there is I'd say a variation that you have to make when you define a makeup air unit. You have to define your set point, because this is not the space temperature set point you're defining. This is the set point at which the heating degree days for that makeup air unit would be defined. And it's typically, and I said last week, that last session, I said, don't really ask why. I mean, we could go into the details, but you have to enter it as it stands now, 2 degrees above your space temperature set point for a normal makeup air unit, unless your makeup air unit supplies at really cold temperature. But if your makeup air unit is a standard makeup that supply between 16 and 18 in the winter, you would define 2 degrees above. And if you don't remember that, you can go back to the slide we had for the first session, and it's spelled out. And you will define the same thing for the unoccupied hours, even though we're going to see our makeup air unit is actually stopped during the unoccupied hours. But just as good practice, you still define it. Now we're going to complete our schedule by entering 16 hours for every day of the week and 0 and 0 for the weekend. Now, there's something missing on this page. I could ask you guys, tell me, what am I missing? It's a critical item that we tend to forget. It's something that often is forgotten, and then we get no results. So the one thing that's missing, and if we go back here, you'll see it. It says that the heating, cooling, changeover temperature is 14 degrees. So this value here, there's no default value for this box in here. So never forget to enter a value. It will actually calculate the length of your heating season and of your cooling season based on that changeover temperature. So if you don't enter it, it doesn't know how many heating degree days basically there is and cooling degree days, so it cannot do its calculation. So never forget, if you see you got no results in your energy calculation, it's often due to a missing changeover temperature. So now we've got our schedule defined. Now, this annoys me to see nothing here, so I don't have to enter it, but it's more of my own personal preference. I don't like leaving that schedule blank, Stephen.
Well, and if you did at some point and you selected the 24/7, all of a sudden we'd be trying to cool and heat the building to 0 because blank is interpreted as 0. So yeah, safety, just put some numbers in there.
So, and I do enter the one that are defined for our base case. Obviously, that base case, if you're doing it for your real makeup air unit, that's information you will need to collect. Now, the next step is to actually define the flows. You remember what Stephen showed you? We define for an air handling unit, we define flows. Then we will define the fan power and the motors separately and the heating section. Talking about heating section, actually, if I want to go in the proper order, I'm going to correct myself. I'm not going to go straight to the ventilation. I'm going to start by defining what produces the heat for that system. And it says that it has a gas-fired heating section. Again, I'm going to go back to what Stephen was showing us. We see that we have a heating section just above the ventilation section. So
you need
we have
to switch screens there, Michelle.
Yes, I'll go there.
Yeah,
so
okay,
we have 80%. So here you see that we have an equipment tab. That's where we will define, if it's a boiler, would be defined here. If it's the heating section, a gas-fired heating section of a makeup air unit, is still defined in the equipment. So you go into where it says step 2, equipment, which I almost went out of step here. I almost went to step 3. But you go to step 2, and you will select furnace. And you could use boiler. It would have the same end result. But again, for clarity, to make sure your model is understood by anybody else looking at it, you will define furnace. And that will be basically your gas heating section for your makeup air unit. So here I'm going to actually change that to gas heating section of MUA. It doesn't have to be that long of a name, but just for clarity. And now it says that in the sheet that I just showed you on the PDF, it says that it's 80% nominal efficiency, and just for the sake of clarity, 80% nominal efficiency. Now I'm going to enter 80% here. Did I make a mistake? Yes, I did, because it says right here, seasonal efficiency, not nominal efficiency. So you can look up what is the reduction in efficiency on gas-fired heating section from nominal to annual, but I'd say you should go at least 5% lower than your nominal. So 75% is what I would enter. Now, if you would say, well, I've got an old system, it's just got one single firing stage on off and it cycles all the time, then you could enter 70%. It becomes your judgment, your professional estimate of what that seasonal efficiency is compared to that nominal efficiency. Now, we do not have cooling in that makeup air unit. It says no cooling section. So we will not define a cooling section. It did say here, by the way, that it is controlled by a duct sensor. So remember last session, said a makeup air unit controlled by a duct sensor is a cold deck system. It supplies below space temperature set point. And that's why I entered 24 degrees supply. Again, it's counterintuitive, but that's how you have to do it to get a proper heating degree days calculation. And this one has a typical set point of 18 degrees, which makes it applicable to that rule of adding 2 degrees to the space temperature set point as the way of defining the schedule for the makeup air unit. So now we've got our heating section, our schedule, our rate. Now we can go to step 3. And
actually, Michel, before
yes,
you, one thing you did there is you put the same value in the base and the proposed case.
yes.
And the other way to do that is to use the copy base to proposed on your top menu there. Yeah,
if you don't want to do it manually like I did, and Stephen, that's a good way of avoiding errors, by the way, what you just just mentioned. So you don't make a typing mistake between the two and get savings or increase. You go always define your base case. Once your base case is done, you click at the top, it says copy base to proposed. And well, because they're the same, you don't see a difference, but it will do it without making human error, like I probably could do if I were to enter everything manually in both base case and proposed case. So we've got our heating system defined. Now we're going to go with the makeup air unit flow. So we go to the energy. And when you click on energy, you've got a bunch of choices. In our case, we want to define ventilation. And that's airflow. It is not the fan motor. It's not the actual motor, because that would be fan, or it could be also electrical equipment. So we're going to define the flow of that system. So we click on ventilation. So you see that there's a new ventilation item that appears, and I'm going to change its name to MUA flow. Again, to be very clear, this is not the fan motor, it's the flow. You've got 2 methods to define the flow. We're going to use method 2, which is quite applicable to makeup air unit. It is not applicable to a recirculation system, a mixed air system, but for a makeup air unit, it is absolutely applicable, and it's actually very simple. So because it is simpler, we're going to go to this method. So you select method 2. You can define multiple systems in there. You could have multiple makeup air units or exhaust fans, but in this case, we have a single makeup air unit. I'm going to call it MUA1, just again, so that for clarity. It's a heating only system, as we saw. So heating only. I only have one of those. And this one, you got to be very careful. You do have to change the schedule. And so we define that MUA schedule. So you guys should all have an MUA schedule. Make sure you change it to MUA schedule. The flow. So I'm going to go back to the sheet, and it says that the supply and exhaust flow are both 5,000 CFM. So I'm going to change that, and RETScreen is great for that. You got so many units that you can change to really match the information you gather on site on your system. So I'm going to go with 5,000 CFM. Now, it does not have heat recovery because we see that when we're going to build the proposed case, we're going to install heat recovery. So I'm going to go and put 0 here. So we actually have defined our supply flow for that makeup air unit. Now I'm going to do what Stephen said, where I'm going to go at the top in the options and go copy base to proposed. And now you see that you make no mistakes. You don't forget anything. Everything has been, put together identically in the proposed and reference case. I'm not going to change the effectiveness or the heat recovery right now because I want to finish defining the system. Then we're going to go to the proposed case and change it. So right now, that's what we have. The heating system, everybody should have the heating system that was defined here because we only have one. Obviously, it was already selected by default, but if you have multiple systems, you would pick the proper heating system. So there you go. We've got our flow. Now, I could go and say, okay, now I've got my supply flow defined, and I looked at my sheet and it says I've got exhaust. So I'm going to go here and define exhaust. Stephen, am I doing something wrong here? Oh, I'm doing something wrong.
Yeah, you're double accounting.
Don't do that. So I was making a huge mistake. The exhaust, by default in RETScreen, when you have a supply, it will be automatically exhausted. So if you define it again, you will end up with 10,000 CFM of exhaust rather than 5,000 CFM. So when you have a makeup air unit, and actually that was kind of a trap in the sheet here, we did on purpose to define both, just so that we could tell you, do not define both. You only define one. The exhaust is automatically accounted for in RETScreen. So that makeup air unit right now is complete. The next step is to go and define the horsepower, the fan motors, because we don't have that yet. The easiest way to do it, and there's two ways to do it. One is to use the actual, if I go back to energy, you could go and define motors. And it's just fine. You can do it like that. It does require a lot more information than you have.
Or fans.
Sorry, I said motors. Sorry, I wanted to say fan.
But you could do it both ways.
Yeah, you could do it. So there's 3 ways really to do it.
Yeah.
You could do it with fan. You could do it with motors. But it requires more information when you do it with fans. And very often when we do, especially when it's your first cut at the model, you don't have that information. All you know is the brake horsepower or just the horsepower of the motor. So the easiest way is to define an electrical equipment. And that's what we're going to do right now. So I'm going to define an electrical equipment to define my supply motor. So I'm going to call it MUA supply motor. And it's always a good idea to define the names properly. If you keep the default, it's faster, but you end up with, 5 electrical equipment and you kind of forget after a while what it can be. So here I'm going to say MUA. I know it's repetitive here, but I'm still going to call it MUA motors. Now you cannot assign a schedule to it. You have to define how many hours per day or per week or per year. Because we're not running 7 days per week, we have to go hours per week. So we have to enter 16 times 5. I'm not good in mental math.
Actually, there's another trick to that one, Michelle. I like to go over to the schedules. If you go into the schedules, right, just pull up your schedule there for the makeup air unit, and it tells you it's 4171 per year. So you can just take the 4171 per year.
Good trick, Stephen.
Yeah.
So because I'm stubborn, I'm going to enter 80 hours per week.
80 hours a week. Okay.
Now, the next place is, okay, I'm going to enter horsepower. And we look at our sheet. It says we have 5 brake horsepower. And I'm going to make a mistake here on purpose. I'm going to enter 5. That's wrong, because that's brake horsepower. It's at the motor shaft, and that motor has an efficiency. So if you enter 5 here, it would take that as 5 electrical load horsepower. So you actually have to divide by the motor efficiency to get from the BHP to the actual horsepower, which would be 5.4. So if you enter 5.4, then you're fine. You could obviously convert that to kilowatt and enter it in kilowatt, but you have to be careful about the type of value you enter for the electrical load. In this case, the duty cycle is 100%. It will run basically at 5.4 horsepower at full load for 80 hours per week. So I'm going to do again, copy base to proposed. Now, this fan is, let's say it's in the airstream, it will have, and even though it has no impact on our results for this time, it is still important to think about that. It has an impact on heating and cooling. If there was cooling, there's no cooling, there's an impact on heating. All the heat from the motor and from the fan goes into the airstream, so you make sure that this is at 100%. So I could decide now I've got another motor, which is my exhaust motor, which is returning that air from that makeup air in it. I could click on plus here, define it here. It would be a mistake because that exhaust fan doesn't have any heating impact because it's exhausting everything to the outside. So what you have to do is go back into energy, define a new electrical equipment, and this one will be your return fan. And the only reason I'm doing this is now I can put that space heating impact. And if there was cooling, I would put the space cooling impact to 0 because it's a return, or actually in this case, it's an exhaust. So it has no impact on heating and cooling. So you do have to define 2 separate elements. If it was the same heating impact and cooling impact, you could just have clicked on plus and define the return motor right here. Actually, I should have said exhaust. Sorry about that. It should be exhaust rather than return. And it's going to be 80 hours per week, just as before. And this one is 3 brake horsepower. Again, you have to go back. If you are good in math, you do that in your head. I am not. So it's 3.3. And you change the unit to horsepower. And it's 3.3 horsepower, electrical horsepower. And now I'm going to do copy base to proposed. And we have our system completely defined. If we go back through all of the information that was here, everything that is here, we have used. So there's a few critical items to remember. Your exhaust flow, don't define it. It's a makeup air unit supplying between 16 and 18. Your schedule will be 2 degrees above your room temperature. Excuse me. And enter the proper horsepower. If you have a motor HP, we'll have a look at that in the next example. If you have BHP, divide by the motor efficiency. And for every items, as Stephen showed, you can see the energy use in the base case and proposed. That's not fuel, that's energy. Obviously for electricity, the ratio is 1. Here we have for gas, we have the energy, not the fuel. So that's not actually cubic meter equivalent of gas. That's before the furnace efficiency. Now, the last item we want to do, actually, if I go into the include measure, like Stephen, you mentioned before, if I go into the include measure right now, you'll see that I'm not saving anything. I'm in fuel save. Obviously, I'm not saving anything. I can go in fuel consumption, and that now takes into account the furnace efficiency. So we actually have no savings. So I'm going to go back here and fuel saved, but we're going to enter our heat recovery, and we're going to enter the cost for that heat recovery. So first thing we're going to do is 50% effectiveness. That's let's say a runaround glycol loop. So 50% effectiveness, we go back to our flow. We go back to our MUA flow, and remember here we enter the heat recovery effectiveness at 0% here. I'm going to enter that at 50% here. Right away, you saw that the consumption for the proposed case went down by 50%. So if I go, and now I was going to forget, what is the cost of that measure? There's different unit for defining the cost. In this case, we actually have a total value. And if you don't know, by the way, there's always those database, and the database cost here, if I click on it, it will give you typical cost for heat recovery per liter per second. And actually the one we're using is pretty much within that range. So $30,000 for heat recovery. And if I go back now into my include measure, it will tell me that my payback is 9 years. It's not great, but nowadays there's people that will definitely look at that measure because it does save a lot of greenhouse gas because it impacts natural gas. But I'm not done. If you said, oh, you forgot something, you would be right. When you put heat recovery, unfortunately, it increases your static pressure drop through your system, both on the exhaust and the supply. And in this case, they tell us that it adds 20%. So I have to go back here on my supply fan motor, and I have to add 20% to that 5.4. So it will be 5.4 times 1.2. So 6.5. So I have to go and put 6.5. Very often people forget about increasing the static pressure drop or the fan power when you put a heat recovery. So you should not forget that. I have to do the same on the exhaust, 20% more.
3.4, call it 4.
I call that 4, yes. Now we have our heat recovery system completely defined. I can go back to my include measure. And hopefully, as you saw that the payback went from 9 to 10.9. So to account properly for the impact of that system on the fan power, it does reduce our payback from 9 to 10.9. So if your payback threshold is 10 years, you'd be just above. You'll get some incentive from Enbridge, so you'll be able to bring it back to 9. But that's the great value that RETScreen will bring to you, is to be able to account for things like that, those what we call those interactive effect, basically. If I had a building envelope defined, then the impact of that, fan motor heat onto the building heat demand would be accounted for, because if you remember, I put this at 100%, so it would consider that. So this slider here, it will have an impact once you define your building envelope, your spaces. So Stephen, I don't know, do you get about the same results as I do?
I get the same numbers, right on the money. Yep.
So that's how you would define a makeup air unit. The only time it would be different is if your makeup air unit is controlled by a space thermostat. So it becomes the main heating system. Then you will define it exactly like the next one we're going to do, which is a single zone system.
Before you jump to that one, Michelle, I just want to explain the nuance here. Just go back to your summary screen there. Some people might have noticed that the simple payback has jumped from 9 years down to 8.7 years for the makeup air unit, the ventilation piece here. Does anybody think about why that could have occurred? It's like there's more energy available in the makeup air, to heat the makeup air. Where is that energy coming from? Well, where it comes from is the interactions between the electrical, that is the impact on heating. So in fact, in our proposed case, we use more energy on the supply fan because of the increased pressure. That energy manifests itself as heat, and that contributes to the heating of the makeup air. That actually marginally reduces your simple payback on that particular item. So the interactions are being taken care of even in this simple example. So
yes. All right. So is there any questions before we go on to our next system?
I would save that one. And somebody asked the question, are we going to, we'll send the solutions out afterwards. I'm going to save that one as case number 1.
So we're going to start, actually, we can keep that one. I think Stephen suggested, instead of rebuilding from scratch, because a lot of stuff we may be able to reuse. So because I've already saved my own solution before, you guys can save it, and then we'll start from the one you have. We'll modify it. In this case, it will be a fairly heavy modification, but we'll modify it, and then you can save it under a different name. So,
And actually, what I would do is I would save it under your case study number 1. Then I
yeah,
would say save it under case number
right
2
away.
right away, because then
Yeah.
if you hit the save button later, you don't overwrite your first one, right?
Yeah, if you by mistake you go Control S, by reflex.
So I'm going to save this as case number 2, right? I'm going to call
Yeah.
this CV, constant volume system, all right? And then we're all set to go.
Yeah. So now we're going to define actually the same system that Stephen showed us. So that one should be very straightforward. It's also, I'd say, the ideal system in RETScreen in the sense that you don't need to do any kind of workaround like we did for the supply temperature of the makeup air unit. So this is a single zone constant volume system. So basically a standard rooftop unit with one zone thermostat. And that's the way to detect that you've got this constant volume single zone system. The room thermostat controls your heating and cooling coils in your air handling unit. So it's not what I called a cold deck system. You probably remember from the first session, it's a switch over system. So let's go in RETScreen and define that system. So first, as usual, we're going to go in location. Right now,
Same
we're
location.
yeah, so we're
Oh,
we're going to go on,
actually,
on location. We're going to go on location.
You
In
fooled me. It's
location.
Guelph.
So in this case, it's Guelph. Again, the difference between Toronto and Guelph in terms of results would be marginal. But if we want to make sure we have the same results, we're going to use exactly the same. So Guelph, Ontario. I'm going to go OK. So now we change our location to Guelph. Facility, we're not changing anything. We're not an office building. Like I said, you could change to any other type of commercial institutional. It would not really change your energy model. So for our case here, we're going to keep that. For the electricity and natural gas rate, they are the same. So yeah, so it is a bit of time saver to keep the same basis for our example. So make sure that you have 45 cents, 12 cents, so we're good to go. Now, where it's going to start being different is our schedule. So in this case, we have a rooftop unit that keeps 22 degrees during the heating and cooling season, and it runs 24 hours a day. And that because there's no indication of if it's a 5 days a week or 7 days a week, we can safely assume this is 7 days a week. So we're going to go in schedule. Actually, I'm going to remove my makeup air unit schedule. I do not need it for now. Actually, I could keep it for a possible measure. Do we have a measure for scheduling? Nope.
I don't think so. No.
So I'm going to remove that. I don't need it. Oh, it's being used right now. Sorry about that. I cannot remove it until nothing of the rest of the elements refer to it. So I'm going to come back later to delete it, to have a clean file, because right now our ventilation system is referring to that schedule, so it will not allow us to delete it. So
which is a good feature of RETScreen.
yes, it's again, it's a nice safety net. When then you know, oh, I'm still using that, cannot delete it. So we're 22 degrees all the time. So we're going to go back 22, 22. And we're 24/7, so that's pretty easy. Balance point. In this case, we're 16. There was questions in the first session. How do you get that balance point? Usually it's through a regression, but like Stephen said, you don't want to deviate too much from that average of, I think Stephen, you said
16.
15 degrees or 16 plus or minus
is
2.
where I would, yeah, plus or minus 2 or 3. Yeah. And really how I use it is I look at the heating cooling season length, even though we sometimes have an in-between season, and I try to partition the year by adjusting that to an appropriate number.
So in this case, we have 16 degrees. So obviously, if before we had 14, and you see that our heating season was shorter at 16, our heating season is longer. So that's how, if you want to, I'd say, to have a judgment call on your changeover temperature. If you've got a building that you know you got to run the boilers longer, that will tell you to go up in your changeover temperature. So that takes care of our schedule. Now we have to define that system. That's a system that has 10,000 CFM and it has 15% minimum outside air. So it's a recirculation system, which we will have to keep in mind, and it's heating and cooling. So in this case, we need both heating, and it's hydronic heating, and we need direct expansion cooling. So if
let's do those first, Michel. Let's put those
we'll
in
do those
first. Yeah.
Yes, we'll do those first. And we have our gas heating section here. We could just redefine it, but it's up to you. I would actually define a boiler, just again to be, by the book, and because we've got hydronic heating, and our boiler has a 75% annual efficiency. They actually tell us. So I'm going to call that boiler. I'm going to put 75%. Now I could try. Yes.
I've answered that question. Yeah.
Oh, okay.
The one about the temperature, we're using 22, not 24.
Oh,
why?
Yeah, because I'm not using that schedule right now.
Yeah.
So I'm using 22 and 22. It's a recirc system, single zone, constant volume. You enter the temperature as they are in the space. The spaces are maintained at 22 degrees. You enter 22. This schedule here, we'll delete it as soon as we can. Same as this gas heating section. If I try to delete it now, it's going to say I'm using it. I can't, because we have to go and modify this system so it stops referring to this gas heating section and to that schedule. But before, we're going to finish the equipment like Stephen mentioned. So we've defined our boiler. So we went to the heating, we went boiler, we defined our boiler. Now we need to define the cooling section of that single zone. I'm going to call it the rooftop unit, the rooftop unit. So we're going to go into cooling, and it will be a compressor. So when you have, a compressed, not a Rankine cycle, but a Carnot cycle, when you have compressors and direct expansion system, you go compressor. And I'm going to call it DX cooling. I could have called it RTU cooling. And in this case, we have a COP of 3.5, and that's nominal COP. So I'm going to reduce that to 3. 3.5 is the nominal COP. The annual COP, I will go to 3. And again, that's kind of a rule of thumb rather than a hard set rule. Just don't enter the nominal value. Sometimes for cooling equipment, by the way, the seasonal value can be higher than the nominal value. It's not common, but if you got, let's say, a really magnetic bearing chiller that runs at low load most of the year, it can actually overperform its nominal COP. So you got to look at what you believe would be the best representation of your annual COP.
And in addition to that, Michel, sometimes with cooling equipment, you have the seasonal COP statement and you have a seasonal energy efficiency ratio, which is another way to state the same thing.
Yeah.
And that's available. You can use that here. For heating equipment, really the only thing you have the heating system performance factor for heat pumps, but for boilers or for furnaces, you have an annual fuel utilization efficiency. AFUE is akin to or parallel to the seasonal efficiency of a heating plant.
Yeah. All right. So we're done with our heating and cooling. We're going to go back, and now we're going to change that ventilation system that is preventing us from deleting those components we don't need anymore. Obviously, if you start from scratch, you won't have that issue. It's not really an issue. So we're going to go and define the ventilation component of that rooftop unit. So it's a recirc system. Remember, method 1 is really designed for recirc system. So we're going to go from method 2, we're going method 1, and we're going to change the schedule if need be, but we don't need to because that schedule is what we want. Oh, by the way, I'm going to go back here because if we don't delete that, it stays in the background. And
it stays in the background. It won't be used, but as long as it's not visible, it won't use it. But clean it up so you don't get mistaken later on.
So now I deleted it. So now I actually should go back into my schedule. I should be able to delete my schedule that I don't need that MUA schedule. I don't need. It's not a makeup air unit. So I was able to delete it. And I should be able to delete that boiler, that gas heating section that I do not need. And by the way I do it, I select it and I right click and I delete the component.
And it's because it's still called out in your method 1, because when you switch from method 2 to method 1, you're going to have to go over to the method 1 ventilation and change that to a boiler.
Yeah. So now I go back here. I'm going to define that as my RTU flow. It's no longer a makeup air unit. It's a rooftop unit. It runs 24/7. We're going to define its actual flow, which is 10,000 CFM. Now, here there's a little trick. You got to look at all your information. I've got 10,000 CFM. My minimum outside air, not my damper opening, is different. Always be careful. Damper opening doesn't mean percentage outside air. Let's say I use the temperature tools or the temperature rules that we talked about, I believe, in the first session. And I calculated I have actually 15% outside air. So I could come here and define 15%. Now, if I keep reading, you'll see that I have a separate exhaust, which serves the same area. That's 1,000 CFM, and that's a separate exhaust. Now, that exhaust is not coming back to that rooftop unit. And in RETScreen, the way to define that exhaust, and we will do that later, will be with method 2, and I'm going to enter 1,000 CFM because it says right here, I've got 1,000 CFM of exhaust. So if I enter 15% here, RETScreen is going to say, okay, 15% times 10,000, that's 1,500 CFM. And it's going to account for another 1,000 CFM, so that will be 2,500 CFM. If you know that your rooftop unit provides 1,500 CFM, but there's 1,000 out of that 1,500 is exhausted by a washroom exhaust. And there's only really 500 CFM going back to your rooftop unit, which is often the case in those small systems, then you really need to change that 15% to account just for the net exhaust, because that 15% in RETScreen will be automatically supply and exhaust. If you've got a separate exhaust defined separately, it will be defining 1,000 CFM intake automatically separate and 1,000 CFM of exhaust. So to be more accurate in this case, you should definitely enter 5% and not 15%. So you need to look at the entire picture of your airflow balance before you enter 15%. And I'll show you why it's so important. So I'm going to keep going down. We do not have reheat. This is a single zone system. There is no reheat in single zone system. It's got heating and cooling because we defined a cooling system. Now, it's 24/7 I'd say by habit. And Stephen, you may do differently.
Yeah,
I always
good
put
practice,
schedule.
use schedule, because later on, and we're not going to use it in this example, but we may change a schedule, in which case we don't have to come back here and change it from constant to schedule. So I always set this to schedule so it follows whatever's at the top of this column.
Exactly. And obviously, because it's 24/7, it's not going to change anything, the fact that we go from constant to schedule, but it will be very useful later on. And it says that the dampers are in adequate condition. So I'm not going to select leaky for the dampers. I'm going to select medium. Adequate condition, it's typically medium leakage. And if you want to know, you got to look at them. You could do a test, but let's say you look at them and you see they have a little wiggle, you see a little bit of light in there, that's medium. And it does not have heat recovery. So now you've got 0%. It's using the boiler for its heating. And it will use the DX cooling. Now I'm going to go at the top here, and I'm going to go copy base to propose so I don't make any mistakes, especially when there's multiple entries like that. It's so easy to try to enter them in the proposed case so they're identical. And now I should be able to delete this useless gas heating section. Yes, I'm sure I want to delete it. There. So now we've got our DX unit, but we have not defined yet our exhaust flow and our motors. So I'm going to add another ventilation, and this one will be my direct exhaust. Direct exhaust, we don't use method 1. I mean, you could if you wanted to, but it's really, there's no need for it. So I'm going to go here, method 2, and I could call it sanitary. And the air that's exhausted, I know that the exhaust doesn't have heating and cooling, but the air that it's exhausting is heated and cooled. So I do still select heating and cooling, and I've got one unit, and that unit, if I read it properly, has 1,000 CFM. 1,000 CFM. Then you go copy paste propose. Now you define your exhaust flow. And like I said before, that exhaust in RETScreen is automatically compensated with the equivalent amount of fresh air coming in. That's why we did not define it in the rooftop unit. It will not go and take 1,000 out of the rooftop unit. So you would end up with 2,500 CFM of outside air in that section of the building, or if it's for a given building for that building.
Just in case anybody's wondering, leaving a blank in the 0 or a blank is the same thing on heat recovery efficiency.
Yeah, but it's good practice to enter it. Oh. I was just about to do it. So now we're going to go and do our fan motor. This one doesn't have a return fan. It's a supply fan motor only. And it's 5 horsepower motor. So this is, you could be tempted to go back here and say, sorry, you have to define my supply motor. So all I'm going to do is say RTU supply fan motor. Say here, I'm going to enter 5 right here. And then I'm going to go copy paste propose, and boom, it's done. Incorrect. That's the horsepower of the fan of the motor, which is not what is going to be the electrical draw. So I'm going to say it's loaded at 75%. So if I estimate that motor is loaded at 75%, then it'd be 3.75, and the horsepower on a motor is not the electrical at the wire. You still have to divide it by the efficiency, if I'm correct, Stephen. I could be wrong here, but I think
you're right.
I'm right. So that'd be I'm going to say 4.1. So the actual result would be 4.1. Now I'm going to go again and do copy paste propose because I just changed something. So now I've got my supply fan, but my schedule is not correct. So I'm going to go here, and it's 24 hours a day. I almost forgot about that. That's the danger sometimes of starting from an existing model, is to forget the data entry that you made previously. So now I do have my and I'm going to change this here to RTU.
Yep.
So we're almost done. What we need to do now is go back here and say we have also the motor for our exhaust fan. Our exhaust fan has a 1 horsepower motor, but we already had an electrical equipment defined for a return fan. So I'm just going to change the name here for exhaust fan. I'm not going to forget this time, exhaust motor, and it runs 24/7. And it's 1 horsepower. So same thing, 1 horsepower would have to be corrected for its typical loading. Don't forget, a motor is never drawing or almost never drawing its nameplate horsepower. So it would be 0.8. I'm going to be doing copy paste propose so I don't make data entry errors. And this one doesn't have any impact on space heating and cooling because it's an exhaust. The other one does have an impact on space heating and cooling. So we have our model. So if I go to the include measure, we're at 0 everywhere because we have not defined any measure. So what's our measure?
Actually, just 1 second. Let's just back up. Can we look at the fuel consumption base case, Michelle, just so give everybody a checkpoint here?
Oh, yes.
Fuel consumption base case. I'm going to check mine. Yeah, everything I think agrees there. I think that we might have an issue with the flow. No, my exhaust fan motor is different than yours. Can you go to your exhaust fan motor? 24.8, 100. Yeah, so I didn't change my hours, as you pointed out. So
Right.
now where I think there's an issue. Let's go back to to the include screen. So why is your RTU flow and your direct exhaust flows the same?
Oh, did I forget to RTU flow 5% of
Yeah,
that?
and then the direct
15.
exhaust.
Oh, maybe I made a 1,000 CFM
No, it works.
heating and cooling.
Yeah, so
Yeah,
5%. That's interesting because if I go back here, so 5% of 10,000 would be 500, right?
500. Yeah,
But
that's
then we
odd.
have,
Yeah.
yeah. Let me think about that one. You keep going.
Yeah. So we'll look at that later, but that's how you would define your system. Now we do have a measure. In this case, we put a heat pipe in there. Heat pipe has a higher annual effectiveness of 0.6 or 60% efficiency. And it does say that there's no change done to the separate exhaust. If you were to put that heat recovery and you were to recover also the sanitary exhaust, that means you would do some reducting to bring it back, then you would actually have to change your model slightly. You would come here and you would enter 60% effectiveness, but now that direct exhaust is no longer separate. It's actually now being recovered. So you would actually delete that, and now you would go back to 15% in both cases, because now that exhaust is totally compensated by the rooftop unit and is recovered by the rooftop unit. So they are not separate anymore. They're basically been, made into a common exhaust or a common return, but it's not. In this case, there's no change done, and that's a bad idea. They really should have done it. We will have to boost our motor by 25%. It's a little
Michelle,
more here because of the type of heat recovery device we have. Yes?
so you're going to go to 15% on your proposed case flow, correct?
No, because I'm not changing the
Oh,
exhaust.
you're not going to change.
If I
Yeah.
were to change the exhaust,
Okay.
yes.
Just
If
to
I
be
were to
clear.
change the exhaust, or you could actually, if you were to change the exhaust, you could go 15-15 in both cases.
Right. Okay.
And remove the exhaust.
Okay, that's what I just wanted to clarify. So we're leaving the exhaust as it is.
And we'll do a test. We'll do a test, see if they were to reduct it, what would happen to the results.
Yeah. And what I'd like to do is explain that 1,000 C, why those two are the same. All right.
Yeah,
Let's
go ahead.
Go to your include screen. All right, to start with. All right.
Sorry.
Yeah. If you go to the include screen, so we see the 52, the direct exhaust and the RTU energies or fuels are the same. And I asked the question why they're the same. Let's go to direct exhaust and we see we have 1,000 CFM, right? We go to the RTU flow and we see we have a 10,000 CFM system flow, 5%, which is 500. But we have leakage. Dampers. We have dampers. If you set the air damper leakage, which I believe tight is 5%, then it'll change it, right? So even though our minimum fresh air is a 5%, this system will not operate below 1,000 CFM because of the damper leakage.
Yes, so you're absolutely right.
So,
yep. Good one, Stephen. Thank you. So now we're going to change our fan motor in the proposed case because we have a heat recovery device. So the RTU motor is now going to be 5.1. And it doesn't change the exhaust fan because the exhaust fan is not recovered. If it was recovered, then the exhaust fan, which would become almost a return fan, would also have a higher fan power. So now if I go back to my include measure, oh, I did not enter the cost. I'm sorry, guys. I'm going to go back to the RTU flow. So we see what is the payback. And you can look at way more than payback in RETScreen, by the way. I'm showing you payback because it's simple to look at right now, but we can look at way more than that. So I'm going to say it's $15,000. So I'm going to put $15,000. Now I can go into the include measure, and I'm going to go in fuel saved, and we have 12.3 payback. So it's a little longer than what we had for our makeup air unit, which actually make a whole lot of sense, especially because we are not recovering that direct exhaust. Now, if I were to recover that direct exhaust, like Stephen said, then I would get 15% recovered here. It doesn't change anything in the base case. Technically, I would remove my direct exhaust. I don't want to do it right now and screw up all my model, but I would remove it, put 15% in both, and then in my include measure, it shouldn't, well, that's because I haven't changed it. I have to change it to be able to get the proper result.
Leave it at the 5%.
I'm going to leave it at the 5%.
Yeah.
But if you do remove your direct exhaust because you're recovering it, then you put 15 in both and you'll have a better payback. It'll go back to around 10 years rather than the 12.3 years because I did do the test separately.
Well, let's just go back to the include screen, just make sure everybody is on the same page there. 12.3 years overall. And again, we see a negative, we see the negative, the increase in energy consumption here, right, on the supply fan. But we also see negative savings on the cooling load because now we have more cooling load because of that increased energy from the supply fan. But in fact, it turns out that there's also a benefit on the heating side of it as well. So basically, the interactions at this point get a bit complicated, but they are there and they are doing or reflecting reality better than ignoring them.
And we haven't looked at GHG, but obviously in RETScreen, you always have the possibility to look at what the measure has in terms of impact on your greenhouse gases. And you see here in green that the measure is reducing your GHG. We don't have time to go into details of that, but it's always there. So you just go into emission and it will give you the impact on GHG. So this is actually a direct, the one caveat here is it's a direct model. Just be careful about your flow balance if you've got direct exhaust and you're not recovering it, because if you don't define it properly, you'll end up with overly optimistic results. So be careful about that. If there was no direct exhaust, like I said, you would have entered 15, 15, no questions asked, very straightforward. The next case is one.
Do you want to bring up the picture of the slide for that case? Do you have that handy there?
Yes, I do.
Just to give people, so the first one was pretty simple. It's your makeup air unit. The second one was your simple constant volume system. And Michelle's going to pull up the slide, which shows the picture of this new system that we're going to look at now.
So what we just looked at is this system.
Yep.
We did not have a return fan. And what was installed was this device, which is a heat pipe. The next one we're going to do, we'll actually have the same heat recovery system. And just so you know, the one we had before, this is the type of heat recovery device that was installed. That's why it had a lower effectiveness. It was a run-around glycol loop. Now, the next system we're going to look at is a constant volume system with reheat. Physically, if you go into the unit, it'll look just like that. The big difference is how do you control that heating and cooling coil. In this case, you've got multiple zones. The zone thermostat controls a reheat coil. And it does not control the heating and cooling duct. Those are controlled, heating and cooling coils, sorry. They're controlled by a duct temperature sensor. So it's a cold deck system for the vast majority of the cases. Rarely is it a switchover system. So cold deck system controlled by a space temperature sensor. Now you have to define it slightly differently in RETScreen to get the proper results. You'll see it's very similar with just a different schedule. If you were there for the first session, you'll see that we have to modify the schedule. So let's go back to our descriptive of the system. So we're going to change the location, the climate data location to go to Ottawa. You know, I want it to be fair. So
you want to start from scratch on this one, just so you're not fighting with,
Yeah, this one's very similar. So I'm gonna start with a new feasibility. I'm not gonna save anything. I already have those saved. So starting from scratch, I'm gonna go back to select climate location. I could just drag that to Ottawa, by the way. I can just go and drag that to Ottawa International Airport. There we go. So I'm in Ottawa. I'm going to have to change the type of facility. I'm going to go commercial institutional, office building. Now go into the energy tab. as before, first thing to do is adjust your rate to your marginal rates, 45 cents and 12 cents. Now, for those of you who may be Class A customers, you would enter probably 4 cents or 3.5 cents for your annual rate. That be the, if you think your measure is going to help on the GA, there can be ways of calculating that, but by default, your marginal kWh rate would be what you pay for energy, which would be not 12 cents. It'd be way lower than that. So just be careful if you are a Class A customer. And if you think your measure are not going to impact your GA or your demand in any significant way. So once we've got that, as before, we go to schedule. So we look at what the sheet says. So it's 14 hours per day, Monday to Friday, with a changeover temperature of 16, and we keep 22. So as before, just for proper definition of the system, we're going to enter anything in the blank spaces. Obviously, the changeover temperature is quite critical. So at 16 degrees, it is. But we don't want 24/7. We want our own schedule. So I'm going to call that CV for constant volume, CV schedule. Now, I could be tempted to enter 22 and 22. 22, 22, then 14. Is it 14, Stephen? Yeah.
14 hours. Yep, correct.
Okay. So for those of you who were there for the first session, you're probably like, hey, that is wrong. And you'd be right. The constant volume system, when you define its schedule to account for the fact that it's a cold deck system, it's really not used for heating the space, or almost never. You do have to change your space temperature heating set point to be more close to what is really your mixed air temperature limit. In this case, the rule would be you go back to your location. You look at your average air temperature, 5.8. You will enter either the minimum of 5 degrees Celsius or 1 degrees above that average. And I'm saying 1 degrees, I try to remember, I think it is 1 degrees. I tested it. I made a bunch of tests on that. My memory is always. So what does it say here? Yes, it is 1 degree above. And so in our case, that would mean that we will enter here 6.8. Now, again, a bit like for the makeup air unit, there's a long technical reason behind that. I'm not going to expand on that, but 6.8, that applies if your outside air percentage is below 20%. If it's above 20%, we would define a different rule. And again, I'm not going to go into details because most systems are around that. They don't usually have much more than 20%. So 1 degrees above your outside air average yearly outside air temperature, or never below 5 degrees, never below 5 degrees. So that would be your constant volume system schedule. You will not apply that schedule to anything else but that constant volume system. That's quite important. Now we're going to go and define our heating and cooling. So it's got hydronic heating with a boiler, and it's got a chilled water plant with an annual COP of 4.5, and the boilers have a nominal efficiency of 80%. So if I go back here, we're getting used to that. We're going to go boiler. We add a boiler, and it's 80% nominal. So we know that we don't enter nominal efficiency. We enter annual efficiency. I'm going to say it's not an atmospheric boiler. If it was an atmospheric boiler without a fan on the burner, you'd enter 70% for atmospheric or lower. But in this case, I'm going to enter 75. We have cooling done with a chiller, but a chiller is really just a compressor. So I'm going to call that chiller. And the chiller has an annual COP of 4.5. So I'm not derating or uprating that efficiency. I'm entering it as is, 4.5. Now, we will now define our ventilation system, which is 15,000 CFM. It's got both a supply and a return fan motor, and it's got 15% outside air. There is nothing that says that air is direct exhaust. So we're only defining that system in terms of airflow. So we're going ventilation, constant volume system. It's a recirc system, so we're using method 1. Important, don't forget to change your schedule. You go constant volume, 15,000 CFM.
And don't forget to change your units. You didn't mention that, but that's a very common error. You did change your units, but just a reminder to everybody out there, set your units first, then put your number in.
Yes, CFM. Now, the supply fan motor, return fan motor are defined in terms of BHP. So 15 divided by 0.94. Oh, that's 16. That's later on. Sorry, guys. I'm already into the motors. I'm too anxious, so
okay, you're good for time.
Heating and cooling, I'm good for time. Okay.
Yeah. So here, if you skipped over reheat,
yes,
you're going to calculate reheat separately in a more granular method. So we're going to set the reheat to off here, right? No.
Exactly. So I would recommend, if you want to maintain flexibility into your reheat calculation, which I strongly recommend that you do, select no for reheat. So we'll select no. I'll show you how to account for reheat in a very flexible manner that will allow you to adjust that rather than use default values. And thank you, Stephen, I forgot about that one there.
So there was a question about the 6.8 degrees, Michelle.
Yes.
So why are we using the 6.8? I mean, there's a long technical discussion behind it, but maybe you can give the Reader's Digest version.
Yes. So when you have a cold deck system, this heating coil, the only thing it does is take the mixed air temperature and heat it to about 18 degrees. But your mixed air temperature is preheated by your return air. You got 85%, in this case, return air, which is already warm. It's at 23 and 24 degrees. And it's preheating that little 15%, excuse me, that little 15% outside air. So until it gets to about -15, that heating coil is going to stay off. And in RETScreen, to be able to account for that and not consider that it's a hot deck system, a hot deck system will heat that supply air all the way to like 30 degrees Celsius. So it's not limited in how it can fire up that heating coil, because it's allowed to heat the air that goes to the space to a very warm temperature, just like a furnace. But a cold deck system is not allowed to do that. It's limited to about 18 degrees. You may push it to 20 degrees. Past that, you're going to have all kinds of issues in terms of comfort. The operators are going to get a bunch of calls. People are overheating in interior zone. So you're limited to about 18, which means that you basically hardly use this heating coil. And in RETScreen, the equivalent way of defining that is using that rule of using 1 degree above that yearly average. And in order to establish that, it was actually through looking at how RETScreen does that calculation and some trial and error to establish that the best way for a system that has, between 5% and 20% outside air to account for that limitation in heating from a cold deck system, the same thing will apply to a VV system, is to use that 1 degree above.
And if you're worried about freezing the space, don't worry, because later on we're going to do reheat, which takes into account taking it up the remainder to get to what the appropriate temperature is for the space.
So that's why we're going to select no here, heating and cooling for our system. Like we said, even if it was 24/7, you would still use schedule. In our case, it is schedule. So we do select schedule because it's 14 hours a day. Let's look at what they said for the dampers. They're low leakage dampers. So we're going to go to tight. And it doesn't have heat recovery. It's heated by the boiler. It's cooled by the chiller. And we're going to go copy base to proposed. Boom, we have the same consumption. So we're okay. Eventually, we're going to put our measure. So we define our ventilation system, the air movement out of it. Now what we need to do is define the two fans. So we're going to go
So
with
Michelle, there was a question.
Yep.
There
Go
was a
ahead.
question about the unoccupied space temperature. Do we set that to 6.8 or leave it at the 22?
Oh, the system is going to stay off, but you know what? Very good point.
Yeah.
Just to be safe, and thank you very much. That's an excellent question. It should be 6.8.
Yeah.
Just in case you forget to put the schedule and you leave constant, at least it will not give you an overestimation of your energy impact. So good point. So for the supply motors, again, you define an electrical equipment, and we're going to call that a supply motor. And I was overly anxious before. I had already calculated.
I would do the same thing, Michelle. So
supply motor.
And this would be 14 hours a day,
it's not
5 days a week, right?
Yes. So for and I'm going to use your trick, Stephen. I'm going to go into the schedule. That's
3650 per year.
3650 per year. So I'm going to go hours per year. I never done that before.
Yeah, and if you wanted to know, like you do the 3650, there's another aspect to this trick. If you're on the 3650 hours per year and you want to know the hours per week, you just select hours per week in RETScreen to do the calculation for you.
Yes, that's true.
But yeah.
So our supply fan motor is 16 horsepower because we had the brake horsepower. I hate leaving it empty. Going to be copy based propose. Boom, we have our supply fan. Now I could add the return fan here. It would be slightly incorrect, but not as incorrect because a lot of the energy from the return fan is recovered. There's maybe 15% that's rejected to the outside. So just to be, as exact as possible, I'm going to define another electrical equipment.
Actually, Michelle, can I show you another trick?
Yes, go ahead.
Just delete that other electrical equipment you just put in there.
Oh, okay. You are going to copy the one that's there. Right?
Yeah, because you can save people time. If you just right-click on the supply motor and say duplicate, right? Yes. It'll create a duplication. Then you can just go and modify your duplicated one for your return.
There's our return fan.
You knew that. I just wanted to point out.
Yeah, well, I never use it. I knew, but I don't use it for some reason. So all we have to change is the size of it. So it will be probably 6 or 5.5, 5.3. So 5.3. Now, don't forget to do copy paste propose. I did change only one thing just to be sure. So let's review here. So we've done all of this, but
you got to change the heats where the heat is because that. Yeah, I guess you're going to have to adjust.
It's 85.
85%. Yeah.
85. Thank you, Stephen. Obviously, for our results here, would not have an impact, but it will have an impact once you define your building envelope. So the percentage I used here is the percentage of return air being returned to the building. So it's a good estimate of how will be the useful heating and and the impact on cooling. So 85%. Now there's one thing we haven't accounted for is those two lines here. We have reheat coil in that system. And the supply set point is 15 degrees in the winter, and 20% of the system has reheat coil. So what I'm going to do is go back into one of the slides that we had the last time. So the flexible method to calculate your reheat is to use this equation, which is a very simple equation. It's CFM. It's all in BTU hours, by the way. CFM times 1.08 times the room temperature minus the supply temperature times the percentage of the flow that will be subject to that reheat. Obviously, there's things in there that you will have to assume. It's not all easy to get, but the equation itself is really easy. So in our case, we have 15,000 CFM. If I'm correct here, that's 15,000 CFM. Our supply is 15 degrees. So actually, this is in Celsius. I should enter that. Degrees Celsius. I do the conversion inside. So I'm supplying at 15. My space is at, sorry about the flipping here, 22.
22.
So 15,000 CFM, 22 room, 15 supply. What's the percentage of reheat? It's 20%. So if I apply this equation, which is this equation here. I just entered it in Excel. It gives me 40,824 BTU hour of reheat. So the way to define the reheat and remain flexible in the way you want to define it is you go back to energy and you will define what's called a process heat. And the process heat, I'm going to use level 2. So I've got a little more flexibility when I do level 2. It will ask me either the kilowatt or the million BTUs. Let's say I want to enter it in kilowatt. I already made the calculation here. So it's 12 kilowatts. So I've got the equivalent of 12 kilowatt of reheat. And I'm going to say 100% duty cycle because I'm going to enter the hours per year that reheat is active. So in this case, it tells me that my reheat is going to be on 7 months a year. So it's 7 months a year, 14 hours a day, 5 days a week. So if I say, and obviously that's an estimate. You could say, well, maybe my reheat is not always active, but if your system is active and you've got 20% reheat, you have to assume when your boilers are on, your hydronic loop is on, you will get that reheat. So how many hours? So you got 7 months, whoops, and you can do it approximately 7 months times, times 5 days per week, and you get problem with my multiplication here.
Times 4.2.
Times 4.2 weeks per month, and times 14 hours per day.
Yeah.
And that gives you 2,058 hours. So you say 2,058 hours, and it's by the boiler, copy paste to propose, and now you've got your reheat load. The nice thing about this is you can change the hours you believe that reheat is on, the percentage of the flow that's being reheated, whereas you could not do that if you were to use the selection box for the reheat that's in RETScreen. You could still decide to not do any of that and use the reheat, and it will give you a reheat load as long as you don't have 0% outside air. It will give you a reheat load. But I suggest that you use this process that we just showed you.
Michelle, I'm going to ask you to do one thing. I'm going to ask you to show people how to record that hand calculation in here. So you're going to go into there. You're going to hit show notes up on the options, right?
Right there.
Show notes, right? And then you're going to go over to your spreadsheet and you're going to just do a screen grab. Just do a screen grab of the formula.
Where's my screen grab? Print screen.
He's going to grab the...
There we go.
Okay, he's grabbed the screen. Now he's going to go over to RETScreen and he's going to put his cursor into the notes. There we go. You can take whatever you want. Airplane mode.
The airplane mode. I put myself in airplane mode for a minute there. So there, yes, you can document how you did all of that calculation in here.
Yeah. So there we go. So he's using the note section. Now you could hand type that in too, but we just did a screen capture like that. So
yeah.
Okay.
So obviously right now we have no measures. As before, we go in fuel save, there's nothing. So I'm going to go and check what the measure is. It's 60% effectiveness as before for our heat recovery device. We have fan power that's higher, and we have an install cost of $21,000. So I'm going to start by just entering the effectiveness. It's the heat pipe, basically the same heat recovery device we had for our previous system. So I'm going to come here and enter 60%. Oops, sorry, 60%. And before I even change my motor, I'm going to go into my include measure. And, I don't have a cost, obviously. That would help. So it's $21,000. So it's a bigger system, a little more expensive. Now I can go in my include measure. And my simple payback is 227 years. I definitely could go and change my fan power, which I should if I want the proper, energy impact, but it's just going to make things worse. So it would actually increase the payback because now my electrical is going to go up. I will save a little more with the heat recovery wheel, but it'll be, a pretty bad investment to do that. And this is not surprising. A heat recovery device on a 15% cold deck system, VAV or constant volume, usually has no payback. So what RETScreen is telling us is confirming that it would be a bad investment to that. It would be a way better investment, as we saw, for a makeup air unit or a single zone system. So if we want to make the change, again, we have to look at our brake horsepower. and increase that by 25%. So I could go into my supply here. That's 16. I'm going to go 16 times 1.25. That'll be 20. Yeah. Thank you, Stephen. Yeah, you're better than me.
Well, I can do that one in my head.
Yeah, I'm not even thinking. I'm just, going to times 1.25, 6.6. And now we have the complete solution with the cost, with the space cooling impact properly accounted for. Thank you, Stephen. And if I go into my include measure, now we see before we had 227 years, now we have none. Why? Because we are now negative. Actually, this is costing us more than not having installed. At least before I accounted for the fan power increase, it was giving us some net savings. Now we don't get even any net savings using the heat recovery on that system. So that is why changing that schedule is so critical. What happens if I keep 22? If I keep 22 and I go into my include measure, it's still terrible, but instead of 227 years, I'm at 18 years. I mean, at least you'd still not select that measure, but it has a large impact. So I'm going to go back to 6.8. So this is our cold deck system. There's one more case we're going to cover, and this time I'm going to use this system as a basis because they are so close that if you don't want to redefine everything, it's much faster to keep your constant volume to change into a VAV because they are twins. They are very similar. So I'm going to go in here and I'm going to go back to location and see what they're telling us about this VAV system. And remember, a VAV system, if I go to the slide that we had before, a VAV system is very similar to our reheat system. So it's a recirc system with our economizer, our mixed air temperatures right here. But instead of reheat box, we have VAV box. But it's a cold deck system because the heating and cooling coils are controlled by a duct temperature sensor, which 95% of the time will be cold deck. So it's supplying below or at most at room temperature. Obviously, in here, you could have reheat coil. It's quite common to have reheat coils. And then the air going into the space can be warmer than space temperature, but the air getting into the VAV box is at or below room temperature. That's what makes it a cold deck system. So I'm going to go back to our PDF. We're still in Ottawa. We still have the same rate. So I believe that's all we already have on here. So this is all good. So we don't have to change any of that. Our rates are the same. Now,
ours is the same.
Let's look at our schedule. Yeah. But I think the schedule is the same, Stephen. So I think 14 hours a day, Monday to Friday. I think I was a bit lazy on this one. I decided to keep the same. So what's important, again, is what is a changeover temperature? It's 16. It's the same. It's a cold deck system. So you use the same rule as the constant volume. You say, I'm using a supply temperature in heating that's 1 degree above the yearly average or 5 degrees, whatever is higher of the two. I will change its name to VAV because we are dealing with a VAV system, but everything else remains the same. Heating and cooling. So hydronic heating, boiler nominal efficiency of 80%, and the cooling plant annual efficiency is 85. Just, out of, it's a caution here, I'm going to make sure we have the right efficiency, 75%. That's correct. Chiller at 4.5, and that's yearly. Always be careful about the fact, is it defined as nominal or yearly? It is nominal. So now we can go to our system. I'm going to change the name of the system for VAV. And it says 15,000 CFM. So I'm going to enter 15,000 CFM. Right or wrong, guys? It's a VAV system. In the sheet, it says it's 15,000 CFM. I guess I should enter 15,000 CFM. That would be wrong because in RETScreen, the ventilation will not account for the flow modulation from your VFD. So you have to enter what your estimate of the yearly flow is. And at the bottom here, they They are nice enough to give us probably an estimate. They say the VFDs run on average at 80%. So 80% of 15,000 is 12,000, isn't it?
I think so. Yep. 1/5 less.
It's the only thing I could calculate it mentally here. So,
well,
so
we,
you
we
enter.
can both agree and be wrong.
Yeah. So 12,000. So that's an easy mistake. Don't forget, VAV system should not be running at 100%. Maybe they are. And if they are, that's a bad thing, but they should not. So you would enter the average flow. And if your outside air is always at the same damper position, you probably don't modulate your damper position based on the VFD speed, which is extremely rare. So you could enter 15%. Let's check if there are separate exhausts on this system. There is no separate exhaust, so you can enter that 15% directly in here. Reheat. There can be reheat. There is often reheat in a VAV system. In this case, just as the previous case, because we want to keep our flexibility in our calculations for reheat, we're going to enter no. And obviously it's heating and cooling, and the system is scheduled. There is a difference, though. I just noted that it says that the dampers are poor quality. So I'm going to go there and put leaky. I'm going to do copy paste to propose. I know I only changed two items. I could have done it manually, but again, it's safer to do copy paste propose. And actually for now, I'm going to remove the cost because I'm going to enter the proper cost later on. And you can always check if it's exactly the same numbers here. You got zero energy save, you know you're good to go. You've got a base case that's exactly the same as your proposed. For the fans, so there's a little thing to do with the fans. It's a 20 horsepower brake horsepower motor and 5 brake horsepower return fan, but it's got a VFD. So you got to adjust that to account for the VFD. So, and that VFD is at 80%. So you're going to say, hey, I'm 20 horsepower, but it's running at 80%, and it's on a VFD. Whoops.
You got to cube that.
Yeah, and as Stephen said, it should be cubed. But because of practical constraint, usually the theory says it's cubed, but I'm going to go with the exponent 2.7. So that motor on average will not draw 20, it'll draw 10.9. Actually, the motor itself will draw more than that. There's a motor efficiency, which I'm going to divide by 0.94. So it's 11.6. So you would have to replace that by 11.6. Quite important to take into account what we call the affinity law. When you have a drive, don't multiply the drive percentage by the brake horsepower or by the kilowatt. Unless you can read the kilowatt on the drive, then you use that. But if you have the motor horsepower or the brake horsepower, you will multiply by the speed, exponent to the cube, or if you're conservative, exponent 2.7. So we'll do the same thing for the return fan motor. I'm going to go there, change my, and I could, like Stephen said, I could cut and paste all of that into the notes. And then I would, because I know I'm going to close the sheet without saving it. So that would actually save all those calculations into the notes in RETScreen. So I'm going to go return fan, go 2.9, copy paste propose. The hours here, we haven't changed the schedule. We're using the same schedule. So I could go check. It's 3650, that same case as we had before. So I know my schedule's correct. Let's see. We've dealt with all of this. 15% outside air, motor efficiency, COP. But there's a little note here. It says that 20% of the distribution has active reheat coils. Aha. So that is just like our last case. Even though it's constant, it's a variable volume. Doesn't mean there is no reheat. There actually is reheat. In this case, it's also 20%, and it's also active 5 months per year. So the boilers are off 5 months per year. So it's active 7 months per year. So same case as before with the same temperature, with the one distinction that our flow is not 15,000 CFM. It is 12,000 CFM because we have to use the average. If you say, oh, I know my average flow in the winter is a bit lower than in the summer, you could actually use a flow here that could be 10,000 CFM if you assume that it's lower over the winter than in the summer. So you could calculate your reheat based on your average winter flow, because that's where your reheat may be more active. Maybe it's active all year round, and then you would enter the average yearly flow. So we have 9.6 kilowatt of reheat using exactly the same calculation. Now, I'm going to go in process heat. I would delete that print screen, replace it with the new print screen without the airplane mode off. And I would document this reheat calculations. I'm going to be copy paste to propose.
Check that.
There you go. Yeah, sorry. And now if I go into include measure, we should be all at 0. And as before, I'm going to go here. And now you guys are not going to be surprised. I'm going to put 60% effectiveness. And it's probably the same price, $21,000. It's the same size system.
Yep.
And I'm going to go back into my include measure before I even put the correction for the fan power. And just like before, actually, the payback is 10 years better than before. So you only have to wait 212 years rather than 222 years to get your money back on this measure.
And it'll only get worse if we add in the increase in load on the supply and return fan.
Yeah, because we'll have, again, if we enter 25% more, I'm not even going to account for any finito loss. I'm just going to take my 11.6 times 1.25. That's 14.5. And you don't forget to do it on a return.
I remember the first time I ever met you, after the original time I met you, Michelle, and we were doing this calculation in a hospital, and you were shaking your head over why they have these heat wheels on these constant or these variable volume systems, and you go, they're not going to save any money.
No. Only when you have lots of outside air. You have to be at 30% plus outside air to get any kind of savings. So now I almost made a mistake by correcting the base case. As you probably noticed, I didn't correct the proposed case. Now, if I go back to my include measure, we see that as before, actually, we're a little better than the constant volume system. The constant volume system had negative total savings and negative total cost impact. In this case, we are still having a 769-year payback. So obviously you would never do that. But it just shows you that how you define your HVAC system in RETScreen will provide you a really good idea of your payback for different type of HVAC system, from a makeup air unit to a single zone unit to that constant volume, which is a worst case scenario, and the VAV, as long as you apply the proper method of defining your ventilation system and obviously all of the other components of the system. So
like I said before, it's about abstracting reality into a fair representation in the software, and then as RETScreen builds itself as making a good decision based upon that result. So so just go ahead, Michelle.
I was going to say that was our last case, guys.
Yeah, so we had an optional case, which I'm not going to go through to the same level of detail just before I turn it back to Megan to close things out. But I will send you this case because it's an interesting one. It's kind of like a makeup and exhaust system, but a very simple exhaust kitchen controlled ventilation exhaust situation where what we're going to do is we'll have a base case where we're running the fan quite extensively. In our proposed case, we're going to improve by using a demand control system where we're going to slow the fan down for 12 hours a day to about a quarter flow and shut it down for the remainder of the time. System cost $10,000 or $8,000. So just very quickly, I'll show you what that looks like in RETScreen, in fact. So if we run over here to our energy situation, we still have our heating equipment as we had before, our cooling equipment. We have the ventilation, but in this case, in the base case, we're running this system at 10,000 CFM 24/7, but in the proposed case, we're running at 6 hours at 10,000 CFM, 12 hours at 2,500, and off for another 6 hours. And then likewise, we have to have 3 regimes or 3 different modes for the electricity running the exhaust fan motor. In very simple terms, I didn't account for the efficiency as Michelle did. I simply had 5 horsepower here. But then the 5 horsepower is at full flow, that's the 6 hours, and I approximate 1 horsepower with the drive, right, for the half flow situation for 12 hours. So coming back to my include screen then, I see savings on both sides of it now. In this case, I haven't added a cost in here. So what I'm going to do here is I'm going to go and enter a cost in here. I believe it said it was $8,000. So I'm going to enter a cost of $8,000 in there. Actually, I did enter the cost. It's over here. So I don't want to enter it over here because that's going to get multiplied through. So I do have my cost in here. So let's take a look here and look at fuel saved. So it looks like this thing pays back really, really quickly in this situation. So, I mean, and demand control ventilation, when you're going from a 24/7 situation to a much more constricted situation, there's some pretty good paybacks on that. So we'll send out that file so you can have a look at that afterwards. The idea of demand controlled ventilation in a kitchen. There's probably other applications for the same kind of thing. I'm going to turn it back to you. Nice sunset picture there, but Megan, do you want to grab the last couple of slides, or would you like me to do that?
I'm good, thank you.
Okay. We had lots
Okay.
of questions going through. Thanks for that, everybody. I mean, I tried to keep up with those, few of those verbally, but we probably have a couple of minutes for any other questions you might want to ask now.
Yeah, there is some time. I wanted to let everybody know as well, we got an update during the session that RETScreen released a new version of the software today. You can go and download that as version 9.2. And your temporary key will continue to work on the new version. I'm not sure exactly what the updates are on this round, but that is available
Yeah,
for
they've
anyone
added
interested.
some things in the custom dashboard. They've added other ways to import data into the performance analysis. I don't think there's many changes in the feasibility, but the custom dashboard, I think they've added in some new views in addition to books, but kind of like newsletters type of thing. So there's some cool reporting features in there. So
Okay, great. And we got some questions about the recording. So I have been recording today's session. We recorded the one on October 30th. Usually we don't email out the recordings, but I think in this case, maybe I will, along with all those RETScreen files, what I will email out is a link to our SharePoint site where you can download all of those large files if you're interested in them. Otherwise, check back on Save Energy's webpage, the training and support tab, and our recordings will eventually be living there. Just a reminder as well, we have technical support available, especially for our efficient electrification toolkit, which we have included RETScreen in. So if you'd like, you can email us at training and support, request a one-on-one coaching session to get some support with RETScreen itself, modeling, or any projects that you're looking at completing. And we will set those up for you.
or you can click on that link there too in the slides.
Yes, there's also a link and a copy of the slides will be included in that folder that gets shared. So if there's no other questions, I just want to thank everybody again for joining us today and being so engaged with the session.
Thank you, guys.
Thanks, everybody.
Thank you. Take care.